Hi guys, welcome back to calculus. Welcome back to the second semester here. So today we are doing the opposite of taking the derivative, and we are calling those antiderivatives. We also sometimes call that integration. The process of finding the antiderivative is integration or integrating. And we're going to look at some examples. All right, so first up, can you find a function capital F such that f's derivative is lowercase f, which is 3x squared? So what function's derivative is going to be 3x squared? Well, we know we're going to have to bring down the exponent. So maybe if this was a 3 up here, we'd bring down the 3, and then one less exponent would give us a 2. So maybe capital F is x to the third, because then its derivative would be 3x squared. That works. But what if it had a constant as well? What if it was like x to the third plus 2? Well, then its derivative, we'd bring down the 3, x to the 1 less exponent, and derivative of 2 is 0, so that would also work. All right, but what if there was another x term? Would that work? So what if f of x was x cubed plus x minus 4? Well, then we'd get the 3x squared, but then we'd get this plus 1 from this x. So that guy's not going to work. All right, so we can have an x to the cube, x to the third, x cubed, and we can also have constants. Doesn't matter what constant we have, but any constant. All right, so any function like that will have a derivative that's equal to the 3x squared, what we started with. So that means the antiderivative of 3x squared is going to be x to the third plus any constant we want. All right, and that's our definition of the antiderivative. It's finding the function whose derivative will equal the original function. All right, so we can add in some notation. So instead of just saying find the antiderivative, we use this. It's like a long stretched out s, which actually meant summation long ago. All right, but that is our integral sign. So if we take the integral of some function f with x being our variable, this little dx tells us what we're using for our variable, that gives us the antiderivative, and we always put a plus some c, and c stands for a constant. Because we can always have a constant, and if we take the derivative of the constant, we'll go back to, it'll be 0, and we go just get that other function. All right, so for instance, find the general solution to the differential equation y prime, or dy dx, equals 2. So the derivative of y is 2. So that means y could have been, let's see, well, what would have a derivative of 2? Well, 2x. All right, but we could also have any constant there. So we could say, 2x plus 1, or 2x minus 3, or 2x plus 100. So we just put plus c, and that c could stand for any positive or negative number. It could be pi, it could be minus pi, whatever. So 2x plus c, because the derivative of 2x gives us back 2, and that constant would go away when we take its derivative. So this is what we call the general solution, because it's in terms of this constant c. All right, so some more notation. So this is called our integral sign. The thing inside of the integral is the integrand. The variable of integration is this variable here behind the d. It tells us what's our variable. So we could have multiple variables, but we treat this guy as the variable that we're integrating. The constant of integration is this plus c part back here. And sometimes we call this, or most of the time we call this the indefinite integral, or the integral. So this sign here is the indefinite integral sign. Then we'll have something later called the definite integral, and it'll have numbers at the top and the bottom. All right, so some basic rules. Whenever we're taking the indefinite integral, we have to put a plus c on the end. And since we said it's the antiderivative, if we took the derivative of the integral of f, that brings us back to the function f. So like these guys kind of cancel each other out. So the integral sign and the dx, those go together. Like the dx is the variable. It tells us which variable the integral sign is using. So if we take the derivative here of the integral, they cancel each other out, and we get what's in here. All right, so these are inverse operations. So if we just had x in here, we would just get x, and that'd be the definition of the inverse. All right, so here is all of our integration rules that are being derived from our differentiation, or our derivative rules. So the derivative of constant is 0, so that means the integral of 0 brings us back a constant. The derivative of a constant times x is just the constant, so the integral of a constant is the constant times x plus a c. All right, if we have a constant times a function, it's just, and you take its derivative, it's the constant times the derivative of the function. So the constant can come outside of an integral sign, is what that does. If we're adding functions inside the integral, we just take the integral of each function. All right, and now here's where we get to our real rules. So the things that you have to remember. So the opposite of bringing down the n and subtracting 1 would be adding 1 and then dividing by this new exponent, the n plus 1. So we get x to the n plus 1 over n plus 1 plus c. All right, now this does not work when n equals -1. We'll have a special rule when n equals -1. So we'll have a special rule when we have basically 1 over x like that. It gets its own rule. In fact, this is going to be natural log of the absolute value of x plus c. All right, derivative of sine is cosine, so the integral of cosine is sine plus c. The derivative of cosine is negative sine, so if we take the integral of sine, the negative moves over here, and we get negative cosine. All right, so it's backwards than it was before with the sines. All right, the derivative of tangent is secant squared, so the integral of secant squared is tangent plus c. The derivative of secant is secant tangent, so that means the integral of secant times tangent is just secant plus c. The derivative of cotangent is negative cosecant squared, so that means the integral of cosecant squared is negative cotangent plus c. And the derivative of cosecant is negative cosecant cotangent, so the integral of cosecant cotangent is negative cosecant plus c. Some of these don't really come up that much, like this guy and this guy. Those don't really come up that much, but the rest of these, they're fair game. Secant and cosecant, they'll have their own rules later on, so will tangent and cotangent. All right, those are a little harder to find. So let's try and do this. So we put the exponent up here, 3x to the first. So the 3 can come out front, and this is 3 times the integral of x to the first dx. So this is 3 times, we add 1, so we get x squared, over whatever this new exponent is, over 2, plus c. All right, let's try this next guy. We can rewrite this as x to the -3 dx. So now it's just x to an exponent. So this means we add 1 to this, we get x to the -2 over -2 plus c. We can leave it like that if we want, or we can try and clean it up, bring the x down. All right, this is the integral of x to the 1/2. We rewrite the exponent there. So we'll get x to the, add 1 here, we get 3/2 over 3/2. So we flip and multiply this guy, so we get 2/3 x to the 3/2. And don't forget your plus c. I kind of left it off there the first time. There it is. And let's see, the 2 can come out front here. So we get 2 times the integral of sine. If we don't remember the integral of sine, we look back here and say, oh, the integral of sine is negative cosine. So we get -2, because the 2 is out there, cosine of x plus c. Can we check our answers? We sure can. We just have to take the derivative. So if we were to take the derivative of this guy, we would bring down the 2. So we'd have 3 times 2x now to the first over 2. The derivative of c would be 0. The 2's cancel out. We get 3x, which is just like what we started with. So you can always take the derivative to check. All right, we can do this for any of these if we want. Like the derivative of cosine is negative sine, so we get -2 sine of x. The derivative of c goes away. The negatives cancel out. And lo and behold, we get what we started with. All right, so now we're adding up a bunch of terms. We can still just do this just like before. So we add 1 to the exponent, so we get 3x to the 5th over 5 minus 5x to the add 1, we get 3 over 3, and we end up with lots of fractions here. X to the first, this was x to the first, this becomes x squared over 2. This 1 just becomes x, because x's derivative would be 1, so we get x, and plus a constant. All right, now we haven't gone over any sort of fractions like this, but we do know how to divide. So we can say that this is the integral of x over the square root of x plus 1 over the square root of x dx, like that. So now we can rewrite this as x to the 1/2 here, and this would be x to the -1/2 dx. So now we just do our power rule here. So this would be x to the, if we add 1 here, we get 3/2 over 3/2. If we add 1 here, we'd get x to the 1/2 over 1/2 plus a c. We can probably clean this up a little bit. 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. There we go. Here, we don't have any rules for this, but we can try and simplify this using trig rules. So we can say maybe that this is sine of theta over cosine of theta times 1 over cosine of theta d theta. And these two together, sine over cosine, that's just tangent. I haven't done any integrating yet. I'm just doing trig rules. And 1 over cosine is secant. D theta. All right, so theta is our variable. And now secant tangent, well, that was just secant, wasn't it? All right, the derivative of secant is secant tangent. I think that was right, yeah. There's our answer. All right, so a lot of times it's easier to simplify first. Like we simplified first on the second one here, we simplified first on the third one here, and then we applied our integral rules. All right, so that's it for basic integration. So those are our basic integral rules. The next time we'll come back with some more difficult integrating techniques.